naught plus some lambda, and then we have this En1. What is our En1? So you should remember this formula. So it is the expectation value of the perturbation. Okay, perturbation Hamiltonian. Clear? So this is a very simple formula. You should memorize it. Okay. So this is what we have figured out. So now let's calculate the correction. Okay. So we need to calculate the correction to the eigenstate or the eigenvalue. Clear? So this N1 we need to figure out, because okay, why we require it? The second order energy, order of lambda square, we have this energy En2, so that depends on what? N. Okay, so we need to figure it out. If I know N1, so I can know the second order correction of the energy. Clear? Let's figure out N1. So let's go back to the equation. Okay. Before doing that, okay, so we know this unperturbed eigenstates, they are complete. Okay, so what is our completeness condition? So let's take the unperturbed states M0. Okay, M0, it is a state, it belongs to this set of states. Although this is a fixed state here, I'm looking the perturbation on a fixed state. Let's say you are having a harmonic oscillator. Usually people get confused when I take the perturbation on a given state. Okay, so you take, let's say this is the nth state, unperturbed state, and you look the effect of the interaction or effect of this Hamiltonian H1 on this very state. Okay, you don't consider all the states at a time. You got my point? Okay. Now I am taking, okay, so this all set of states, these all states, they are complete. Okay, and that means, so let's denote them by M0. Okay, so this condition is such. So you are having, so these M0 are the unperturbed states. Clear? Now I can expand this N1. So I can expand any arbitrary state in terms of these states, this basis state. Clear? So if I know a basis set, I can expand any arbitrary wave function, what you know, in terms of this basis set. Clear? So this is a standard principle. So what is unknown to us? N1 is unknown to us. So let's okay, let's expand this N1 in terms of this basis set. Okay? Clear? Okay. So let's do this thing. So you are having this N1. Let's do, okay, so let's insert this completeness condition like this way. Clear? Got it? So this object is 1 and 1 is back. Okay? So there is a sum over M. Okay. So now let's expand. Let's take a term. M is equal to N. Okay? In this very sum, we will take out one term while M is equal to N. So it is like this thing. N0, N1 plus summation M that is not equal to M. So now this sum does not contain what? M term. Clear? Got it? So why? What is the reason for this thing? So since we are looking perturbative effects on this very state, clear? And I am picking out that very state out of this very sum. Because in this M0, okay, so M0 is there, clear? This very state exists there. Okay? Got it? And you know, by definition, yesterday we have said this object is equal to 0. You are having only one state, that's N0, on which you are looking the perturbative effects. So the overlap of N1 with that state is equal to 0. Okay? So that, okay, so this object is equal to 0. So in other words, I can write now this N1 in terms of this M not equal to N. Okay? Any problem in understanding this point? Okay. So everybody satisfied? Yes. Great. Okay. So now what I need to calculate? So this is not 0. This object is not equal to 0. Okay, this is a non-zero quantity. And this is unknown in this very equation. This kind of overlap I need to figure out. Okay, so let's go back to the equation at order of lambda. The equation what we know. So what is that? So we are having this equation at order of lambda n1 hi n0. Is that true? So that's equal to E n0. Just tell me n1 plus E n1 n0. Clear? Okay. Is this equation? Okay, good. So what I need here, m0 n1, this kind of overlap. Why from it will come? Huh? So it will come from here, is it? So that means I have to multiply this very object on left by m0. Clear? Okay, so let's do that. So I'll be having this m0 h0 n1 plus, okay, n0 h1 n0. So that's equal to E n0, okay, m0 n1 plus E n1 m0. Sorry, m0. Okay, now what about this very object? Okay, so this m0. So m0 is not, okay, so m is not equal to n here. Clear? Got it? Now anybody? What about this very object? m0 n0 overlap. What is that? Huh? What is this overlap? Just raise your hand. Answer. What is this overlap? If you are not able to figure it out, this overlap, then there is a problem in your understanding. It is 0. Look, m0, n0, it could have been delta mn, is it? Clear? It is like this overlap. You are having unperturbed states m and n, so it will be simply what? Delta mn. I have put m0, n0 here. Clear? But n is not equal to n in this very equation, because I require a term where m is not equal to n. Got it? So what it would be then? So this is simply equal to 0. Okay, so this is a term what I require, m0, n1. Clear? Everybody? Good. So what about this thing? This h0 will act on m0. What it will give me? It will give me em, okay, not like this thing, m0 n1. So plus m0 h1 n0. That's equal to, okay, en0 m0 n1. Okay, so now let's work it out. So you are having this m0 n1, that's equal to minus m0 h1 n0 divided by, okay, so since you are taking this on this side, so it will be simply em0 minus em0. Okay, so these are the unperturbed energies corresponding to mth level and corresponding to nth level. Okay, now look here. So why m is not equal to n? So you are having this very factor arising in the denominator. Okay, so if m would have been equal to n, then this blows up, is it? So this diversion is there. So that's why we require, so when m becomes n, that means the levels become degenerate. We require actually more sophisticated tool to handle degeneracies. Okay, that we are doing within the degenerate perturbation theory. Okay, so let's try it then. So therefore I can write this n1. So n1 I can write summation m not equal to n. So there will be now a minus sign coming from that. So let me put this very factor first. So it is simply m naught h1. Okay. So this is the first order correction to the wave function. Got it? Any problem? So now let's go to the second order correction to the energy. Yes? Okay. So we have now second order correction. So En2, that's equal to N naught H1. Clear? Now use N1 from here. So you will be getting minus summation M naught equal to N. Okay. So let me write, okay, this way, let me put minus. So let me first write this in N naught, then you are having this H1. Okay, then you are having this very summation. Okay, summation M naught equal to N. Okay, so then you are having M naught H1 EM naught minus EM naught. Okay, clear? So now this is a number, you can pick it out. So it is M naught equal to N. Okay, M naught H1 N naught divided by minus En naught. Okay, then you are having N naught H1. So this will act on this very state. So you are having like this N naught H1. Clear? Got it? H1 is Hermitian quantity, is it? Okay. Now look here. So if you see this very object and this, they are Hermitian conjugate of each other. Huh? They are conjugate terms. So I can write it in minus like this thing. Anybody? Mod of H1 and naught. Okay. So this is your second order correction. Memorize this very formula. So the home assignment for you people is calculate N2 and E3. Because E3 will depend on what? N2. Okay, you need to calculate N2. Okay? Proceed. So, what is our expansion of the eigenstates? Let's look at the normalization. Huh? So, normalization of this N. Okay. So, you are having this very state at N is equal to. Okay. So there is an important point when you try to figure out the normalization. You start with a normalized eigenket on which you are looking at the perturbation. Clear? Got it? The unperturbed state, what you start with, you assume that normalize it. If it is not normalized, then normalize it first. Clear? Then when you try to do the normalization of the total state, this, the perturbed eigenket, you do it at, separately at all orders of the perturbation. You don't take the normalization of the whole wave function. You look, okay, so let's put it this way. So the zeroth order correction is already normalized. Then you look for, when you put the first order correction to the wave function, then you normalize the wave function. Clear? Total wave function. Now you put the second order correction to the wave function, then you normalize the entire wave function. Clear? At all orders of perturbation, you look for the normalization separately. Okay? Got it? So here I am trying to figure out the normalization up to the second order of perturbation. Okay? And try to figure out what is the interpretation of this normalization constant here. Clear? Got it? Okay, so you should actually get an idea for the normalization constant here. Okay? What exactly it means. Look here. So since you start with some energy level N naught, is it? So this N1 contains a mixture of all other states. So that means if you are doing the perturbation to the system, so this particle, let's assume you are having the particle in certain state, this particle goes into all other possible states allowed by this very equation, because this m naught goes from, let's say, 0 to infinity, where one state is not equal to this n naught. Okay, so it makes transitions to all the possible states. Clear? So in other words, there is a leakage of this very particle to all other states. Okay, when I look at the normalization, what normalization usually gives you? That gives you the probability. Is it? Unit probability. Okay, if I look at the normalization of this n1, that should actually give me the concept of the probability of a particle leaking from this m0 state to all other states, or a probability of figuring out the particle that is in a given perturbed state, okay, and its existence in other unperturbed states. Got it? Okay, so let's write it first, then maybe you can get it. Okay, so let me put it here. So let's define our normalization this way. So this is your perturbed cat, okay, and let me normalize it. N means a normalization here. Okay, so let me write a number, z raised power half, okay, like this thing. Okay, so this is an unnormalized perturbed cat. Clear? Got it? So where I am saying if this is normalized, this has to be equal to 1. Clear? Got it? So now let's okay. So what is this z? So let me write an n here. So this zn we call as a normalization constant. Clear? So now let's multiply this one by n naught. So n. So n naught is the unperturbed state. Clear? Okay. So I'm having this way. So you are having this zn and half. Okay. So what it is? N naught. Clear? Got it? Okay. So this is a. I have put half deliberately here. You will see why half is here. Okay, because when you put it in this fashion, star and this one, so it will get what? 1. Clear? Okay. So it is Zn half. What is this N1? Now tell me, what is this N? So it is N naught plus lambda, N1 plus lambda square, N2 plus Z. Clear? So what I will get? Okay. So N naught, it is 1. N naught, N1 is 0. Okay. So it means you are having this Zn half. So this gives you the interpretation of this normalization constant. Clear? So what you get? Zn half is equal to what? N naught N. What this overlap means? So it's a probability amplitude. Is it finding out the particle that exists in this normalized eigencat? You are trying to figure out what is its leakage into the state N naught. Clear? Got it? Or you can say, if you are having particle already in N naught, okay, how, in which states it goes other than this N naught. Clear? So you can, so that means this Zn, it's actually the probability like this thing, N naught N. Okay, so let me write this thing. So it can be regarded as probability of finding as the possibility of finding, okay, for the perturbed state in the unperturbed ones. Clear? Okay. So now let's calculate this Zn. So we call this Zn sometimes as wave function or normalization, or wave function renormalization. Renormalization means correction. Huh? Okay. So it is sometimes known as wave function renormalization. Okay. So let's calculate it. So let's go to equation 1, this equation. So this is equation 1. So try to figure it out. So I am having this n, okay, n. So this is equal to 1. So or I can write like this way. You are having this Zn and n, that's equal to 1. Can I write it? Can I write it? Simply. Because you are having this n in terms of this n. Okay, so half the root goes. So or you are having this Zn raised power half. So it is, sorry, raised power minus 1. So it's equal to 1. So they have to be inverse to each other. Clear? Is it? Okay. So you should not, you should respond. So is it clear? Okay, good. So what I can write it, what is your n? So this is n0 plus some lambda n1. Okay. You can put lambda star. Okay. But I will not use that. So n2 plus dash dash dash. Okay. Then you are having this n0 plus lambda n1. Okay. Plus lambda square n2 plus dash dash. Okay. So let's write. So n0 is 1. Then you are having a term. Okay. So n0 n1. This is 0. Clear? n0 n2 it is equal to 0. So it goes up. So now you are having lambda. So this n1 n0 it goes. Clear? So what sustains? Lambda into lambda. So it's lambda square. Then you are having this n1 n1 will go only up to the order of lambda square. So ignore lambda cube here. Clear? Got it? So I already now know. So that means the normalization of the wave function, it depends on what? The overlap of the first order correction to the wave function. Got it? Okay. Yeah? Okay. So I can write it as 1 lambda square. What is your n1? You have figured out. Just look at your notes. What is n1? So it is minus. So it will be 2 times minus. So that's 1 plus 1. Okay. So then what I can write here? So let's write this n1. So it is equal to, just tell me.
Not equal to.
Okay, so I will write, it will be like this thing, m0 equal to n mod of m0 h1 n0 mod square. So since there are 2 energy factors, 2 times m0 minus en0, okay, it will be now square plus order of lambda. Clear? So you take one n1 and the another n1, so they are conjugate to each other, and the m0 there, that will be actually 1. One summation will go because of the delta function. Clear? So there will be actually 2 summations. So n1 has one summation, n1 has another summation. Clear? So you can have, let's say, m0 here, and then you can write m0 prime here. Clear? So one summation will go because of the delta function. Okay? So if you are not able to understand, shall I show that step?
Yes, sir.
Huh? Okay. So it's like this. What is your n1? Just tell me. Minus summation m0 equal to n. So you are having m0 h1 n0. Then you are having, let's say, m0 divided by em0 minus em0. Okay. So let's write this one n1 n1. So what it will be? So since you are having already this m as a dummy variable here, let's put the another variable k. Okay, so you will be having, let's say, k not equal to this n. Then you are having summation m not equal to n. Okay, with this thing. So what you are having, it is the conjugate. So you will be having n naught h1 k naught something divided by e k naught minus e n naught. Okay, so this will be from where? From this n1. Clear? And then you are having this m naught h1 n naught divided by e m naught minus e n naught. Okay, then you are having this m naught. So there will be actually a cat k naught. Clear? So you will be having cat k naught here as well. So what about this thing? So it will be simply delta k. So once you sum over either m or you sum over k. Okay, sum over k will be replaced by m. Okay. So then you are having only once. Got it?
Yes.
So now, so what I need to calculate Zn, not Zn inverse. Okay? So you can write, which implies therefore Zn. So it means actually it is 1 divided by this thing. Clear? Since lambda is a small quantity, this object is a small quantity, so you can make a Taylor series expansion or binomial expansion rather. So it will be simply 1 minus lambda square by 2, only lambda square, summation m naught equal to n, m naught h1. I should put approximately because I am ignoring all higher order terms. Okay, so it is something like you are having Zn inverse is equal to 1 plus, okay, let's say lambda square sum f. Okay, so you can write Z is equal to 1 plus lambda square f raised power minus 1. Can you write it? So let's expand it. It will be 1 minus lambda square f plus higher order terms. Clear? So that's why I have put a minus. So now look here. So you are having the first, okay, so where from the correction comes? Second order. So the correction to the wave function is from where? There is a second order contribution. Okay? And you see, so this is the usual normalization. Okay? And, okay, so if you see there is a sum over m, so that means the states get leaked to the unperturbed states. Okay, so there is some probability of finding this perturbed state into the unperturbed states. Clear? Got it? And you look here, so there is actually square of this energy here. In the second order correction to the energy, you don't have the square. This factor is there, and this factor is there without a square. Is it in the second order correction? Okay, good. Yes. So if you are having, if the Zn represents the probability, clear? What are the values of the probabilities? Limiting values? 0 or 1. Okay, 0 to 1 you are having probability. So what is the maximum value of this Zn? 1. Clear? You can put lambda equal to 0. So if lambda, okay, so in other words, you can have the Zn is less than 1. Clear? So you can make the probability 0 just by adjusting this. Okay, so if you put this equal to 1, if that means if this object becomes equal to 1, the probability goes to 0. Clear? Got it? समझ आओ? Okay. So we call this sum. Okay, so this is often in literature known as the wave function renormalization function. Clear? Got it? So let's move to, let's look at where the perturbation theory is valid. Huh? Then we'll go to the examples. Huh? Shall we take first examples? Okay, let's take examples. Huh? Then maybe we can, so that you can understand. So let's look at the first example. Okay, you are having the harmonic oscillator as usual. So let me write half of m omega square x square. So this is your what? H naught. Clear? And then there is some perturbation. Let's say alpha x square. So that means you are having this thing. Okay, so you call this as H1. So what are the dimensions of this alpha? No. So alpha x square is having the dimensions of energy. What are the dimensions? Energy by length square. Is it? So usually when you can think this alpha very small. Okay, so this is the parameter lambda what we are considering. Okay, you can consider this alpha to be parameter. Okay, but I will not take this alpha to be the parameter. Later on we can see in a given theory, okay, what these factors are, what they mean. Okay, so we need to interpret these factors later on. Okay, so now let's look at the first order correction. So you know what is your Hamiltonian H naught. So it's H naught when you quantize it. So it's like this thing, and your unperturbed eigenstates, those are N naught. They give you this E N naught. Okay, N naught. What is the energy? Here unperturbed. You should know first what is the unperturbed energy. Clear? Okay. So I'll not put naught here. So I have just put naught in a sense. It means it is an unperturbed state. Otherwise, you can do away with this naught. Then you can put the N, what we are using to perturbed, put a P there. It's a perturbed state. Clear? Okay. So now what is our this thing in this very representation? Okay. So in terms of annihilation and creation operators, so I will write this H1 as alpha. So it will be root of H cross by M omega A plus A dagger whole square. So there will be square as well. So let's put this constant as beta. So it will be A square plus twice A dagger A plus 1. So this I have shown yesterday. Okay. So it is the expansion of this very operator. Okay. So now let's calculate the first order correction to the energy. So En1. So what is that equal to? N0 H1 N0. So this is the first order correction. Okay. So you put this beta outside, it's a number N0. So it is A square plus twice A dagger A plus 1 plus A dagger square. Okay. Okay. So you are having now N0. So let me put this way. What is A square doing with the N0? You have to apply it twice on N0. Clear? So when you do, okay, so let me show. So you are having A square acting on N0. So it is something A0 and A will act on N0. So you will get N0 and N0 minus 1. Then you apply this A0 on this thing. So you are having N0, N0 minus 1. So it will be N0 minus 2. Clear? So you will get from here, so root of N0 into N0. Sorry, not N0, I will use N. So, because I am using N here. So, I should put not use not. Because these are numbers, they are nothing to do with the things. So, since this is a number operator, so you can write this as a number operator. When number operator acts on this N0, so you are having number operator acting on N0, it will give simply the number N0. Clear? It will just count the labels. So it will just count its label where it is. So it is twice N plus. Then you are having 1 will not do anything with this. Oh, sorry. So it will be here N0 minus 2. So here it will be 2N N0. Then you are having plus 1. It will be N0. Then you will be having A dagger square. A dagger will act on first this N0. You will get root of N plus 1. Then you are having the state N plus 1 here. So it will you will get N plus 2. Clear? So it will be simply N plus 2. Okay, so now let's look at the overlap. So this N0 and N0 minus 2, which is equal to 0. Clear? So then you are having N0 and N0, it's equal to 1. Clear? N0 and N0 equal to 1, and N0 and N0 plus 1, sorry 2, that's equal to 0. So you can have like this thing, beta, so twice N plus 1. So this is your first order correction to the. So now let's look at the first order correction to the wave function. Okay. So what is our N1? Okay, just tell me. It's minus summation M0 equal to N M0. Okay, H1 N0 divided by EM0 minus EN0. Okay, N0. Clear? So what I need to figure out? Okay. So I need to look at the correction to the wave function. If I know this correction, I can know the correction to the energy, second order correction to the energy. Okay. You can do directly using the formula of the second order correction, okay, but it is simple to do this way. You go systematically. Okay. So now, okay, so let's calculate this M naught and this very overlap. So you need to calculate this kind of overlap. Okay. Okay. So you have an idea here. Now look here. So when this H1 acts on M naught, so you are having this is H1, it is acting on M naught. Clear? So what are the states it is giving me? All these kinds of states. So let me write. Okay. Okay. So you are having this H1 acting on N naught. Is it? Because there is a sum over M naught over N. So you are having all these possible states M naught. Okay. So what it gives me? Root of N into N minus 1, N naught minus 2. Then you are having 2N plus 1, N. Okay. So this one, 2N plus 1. Then you are having root of N plus 1 into N plus 2, N naught plus 2. Clear? So this is your action of H1 on this unperturbed state. Okay? Now look here in this very sum. So in this sum, M is not equal to N. Clear? So that means if I take the overlap, let's say you are taking overlap M naught. So I need to, okay, so I need to look at the number of M naught states which will contribute. Clear? In this very sum. Okay. So let's take. So this M naught should be equal to, since you are having on this very side, so the first state is actually N naught minus 2. Clear? So that means this M naught must be equal to N naught minus 2. Clear? So this is the first state. So that will be non-zero. Now if you look at N naught, if you take a look at this thing, but M is not equal to what? N. So that means this term will not contribute. Clear? So another term is what? N naught plus 2. So in this very sum, there are only two terms which are contributing. Clear? Okay, so I will write therefore, this sum will be like this, and let's put minus outside. So it will be N naught minus 2, H1 N naught, okay, plus N naught plus 2, H1. Okay, sorry, I should put denominator here. So what is M here? The index M is actually N minus 2, okay, minus En naught, okay. So the here it is actually En plus 2 minus N. Clear? So the N, okay, M equal to N, that does not contribute. Okay. So let's calculate it. Okay, so now it is easier to look. So H1 acting M naught. So this is the term which will give the non-zero contribution. So it is root of N into N minus 1. What is in the denominator? En minus 2. We are doing with the harmonic oscillator. So it is H cross omega. So for N you have to replace N minus 2 plus half. So minus H cross omega N plus half. Clear? So then you are having plus. So you are having root of N plus 1 N plus 2 divided by, so it is H cross omega N plus 2 plus half minus H cross omega N plus half. Clear? So everybody got it? Everybody? Huh? Okay, look here. So what is your, okay, so this is, everybody got this factor, huh? So numerator everybody got, huh? Any problem? Good. So you are having now En minus 2. So what is your harmonic oscillator energy? H cross omega N plus half. So what is the index here? N minus 2. You replace N by N minus 2. Okay? Then you subtract it by En. So what is the unperturbed energy? H cross omega N plus half. So these are actually unperturbed energy corresponding to N minus 2th level, and this is for the nth level. Now you are having En plus 2 here because you are having N naught plus 2 here. Clear? Okay, so what it is? N plus 2 plus half. Got it? Okay? Okay. So now let's write it. Okay? Okay, so we are here, we are calculating what? N1, huh? So therefore your N1 is equal to, so now let's look at this very factor. Let's look. So what you are getting here? Minus twice H cross omega, is it? H cross omega N plus half will cancel with this thing. So here you are getting twice H cross omega. So it is like this thing, root of, we have forgot one factor. Eh? What is that factor? Because H1 contains that alpha, is it? So there is a constant that beta multiplying everything. Eh? Okay, so I will write that constant here. Eh? So minus beta. Please look at that very constant. Eh? So you are having minus beta here. Eh? So the constant what we have calculated in the first order correction. Eh? So that number. Eh? Okay. So then you are having this root of n into n minus 1 divided by minus twice h plus omega n naught minus 2. Then you are having plus root of n into n plus n plus 1 into n plus 2 by twice h plus omega n naught plus 2. Now look here. So you are having the unperturbed state where into two perturbed states. So there is a probability of locating this very state where in n naught minus 2. It is actually the linear superposition of two unperturbed states. Okay, n naught minus 2 and n naught plus 2. Clear? Okay. So this is your, this n1. Now you can calculate therefore. So now let's calculate the second order correction. So that is n naught h1 n1. This is the easiest way. Okay? Is it? So this is second order correction in terms of n1. Is it? Huh? Now you have to apply this h1 on this object. Clear? समझ आओ? Have you got it? Okay, so what is you are having minus beta? Okay. So let me write this very constant as something. Okay, so you need to figure out the, okay, so rewrite, so let me write this thing, n naught, so you are having minus beta outside. So h1, what is h1? That is having beta, this a square plus twice a dagger a plus 1 plus a dagger square, okay? So this is your h1, then you are having n1 like this thing, so root of, so it is minus the root of n into n minus 1 divided by twice h plus omega n naught minus 2 plus root of n plus 1 into n plus 2 divided by twice h plus omega n naught plus 2. Now first thing, so let's look at this very term, twice a dagger a plus 1. So a dagger a will, when it acts on this thing, it will keep the cat same. It will not change the cat, is it? Because this is a number operator, it will not change the cat. Clear? So when you apply this very object on these states, okay, so these cats will remain same. So when you make them overlap with this n naught, so that will give you 0. Because you are having n naught here, n naught minus 2 and n naught plus 2. So it will not contribute. Now what is, okay, so now let's look at this a dagger square. When this a dagger square acts on this thing, so forget about the constant what will come. So a dagger will increase the level here. So a dagger acting on n naught minus 2, it will be first n naught minus 1. So then again acting on a dagger, it will go to n naught. Clear? So that means this will give you the non-zero term with this n naught. Okay? So now look at this a square here. So a square, first a will lower down the state by 1 and then it will again lower down by 1. So where do you get? You land where? N naught. Clear? So these will give the non-zero terms. So you will be having the non-zero terms like this thing. So beta and beta, it is minus beta square. So you will be having n naught, this very thing. So a square, so this root of, so n naught minus 2 kind of thing, and there is this root of n into n minus 1. I will not evaluate this whole thing, so you have to do it at your places. And then you are having this root of n plus 1 into n plus 2 by twice h plus omega. So you are having n naught a dagger square and n naught plus, it is a dagger square, okay, and here it is a square. And you evaluate this actor, this a and a dagger, so you will get those numbers, those factors you will get, so you will get the second order correction. Clear? So similarly, you can now calculate the wave function in renormalization. Okay? So you can calculate what is Zn. Okay, Zn is what? It's actually the overlap of this thing. If you remember, you are having this Zn inverse is equal to 1 plus this lambda n1 n1. Is it? So you have to make the overlap of this state. Clear? You have to take the overlap of this state with itself. You will get n1 and n1. So then you calculate Z1. Sorry, Zn. Clear? Got it? So this is how we calculate these objects. Now the home assignment will be, so you calculate, so if your perturbation is, let's say, alpha x raised power 4. So you have to put x in terms of a and a diagonal, then make it as 4th order combinations. Clear? Got it? So now let's look at this second order. Okay, so let's look at the validity of this perturbation theory. Okay, so we said, so if you remember, we had this h of lambda is equal to h naught plus lambda h1. And we argued, so this term, this perturbation must be small. Clear? So how small it should be? We need to quantify it. For that matter, we will take a simple problem of a two-level system. Okay? We'll consider a two-level system and understand the order of magnitude of this term. Clear? So how small it must be. Okay, what is the two-level system? What is the two-level system? So it is having only two levels. Clear? So give me an example of two-level system. Or when we can idealize a given system as a two-level system. Yes? Huh? Simple example. Semiconductors are very zero. Huh? Much two-level system. Yes, hydrogen. When I can consider hydrogen to be a two-level system. Not hydrogen, an electron in a given electron, an electron in a given potential, you can consider it as a two-level system when? Huh? You have to think. Think of. Masura Thomas? Anybody? Huh? When I say a two-level system, what has come to your mind? What? So this is a problem. You don't think. You just read. You don't think. What has come to your mind when you... Okay, tell me. No idea? Okay, I am saying harmonic oscillator is an n-level system. What does that mean? How many energy levels? So you are considering this very particle in such space where it is having n levels. Energy levels are n in number. Okay, how many energy levels are for the hydrogen atom? Yeah? Infinite in number, is it? It all goes from 0 to infinity, is it? In principle. Okay. Now let's say if I consider, think of an electron. If electron in a potential, let's say for the hydrogen atom, if I suppress all the degrees of freedom except spin degree of freedom, okay? So how many values for spin for an electron? So you are having only two components. A spin up is having one energy and a spin down is having another energy. So you know that splitting through a Stern-Gerlach experiment, is it? So you will be having spin up, So it will be having half of H cross, and spin down you will get minus half of. So there is a level splitting of how much? H cross. H cross omega, let's say omega is H cross omega is the energy. Clear? So if I suppress all the degrees of freedom of my system and only work with these 2 degrees of freedom, spin up and spin down, how many levels are there? So you are having a 2-level system. Clear? Got it? Okay. So any other example? You can think of a 2-level system. Now I have given you. 2-level systems has got, I think, 3 or 4 Nobel Prizes. Okay? So, and it is the, what, 2-level system is a workhorse for a physicist. You do any kind of calculation, do with the 2-level system. Okay? So everything comes with this 2-level system. You are doing experiments, you do with the 2-level system. Okay, any other example you can think of a 2-level system? So you have a photon, is it? So how many polarization it does have? 2 linear polarizations. Clear? So how many levels then you are having? So when you only describe your photon in terms of the polarization states, so that means you are having an effective 2-dimensional Hilbert space. Okay, it means you are having a 2-level system. Clear? Now let's say if you are having a harmonic oscillator. Clear? So all the lines are equally spaced. How in, okay, let's say forget about electron for the time being. I am having a harmonic oscillator. And I am saying how I can make it as a 2-level system. Clear? So what you can do? Because all the levels are equally spaced, is it? You cannot pick and choose only the 2 levels. You can't, is it? So you can say, let's say I can take the ground state and the first excited state and forget about, but you cannot forget them in a sense because they are of the same spacing as you are having the ground state and the first excited state. Clear? So how you can do it? How you can make it as a 2-level system? So you think, let's. So when I say the 2-level system, what I mean? I require only 2 levels and eliminate everything, is it? So if I am saying for harmonic oscillator, I have to make it as a 2-level system. What I need to do? Eliminate other states, is it? You consider only how I can do that. I make a gap between, let's say if I need only the ground state and the first excited state, clear? All higher other excited states I need to eliminate. How I can do? I can increase the gap between first excited state and the rest of the states, clear? So that means I need to put enharmonic terms in the harmonic oscillator. It will simply shift to the energy levels, okay? So the gap will increase. Once you increase the gap, so you maintain the gap between, let's say, the 2 levels what you are interested in, clear? So what you have got then? You have got an effectively 2-level system, okay? You have heard about the LC oscillator? Okay, you have done it in the electrodynamics, okay? LC circuit, you know? Okay, a little. Okay, so you have done the Bose-Einstein condensation? Huh? You have done the Bose-Einstein condensation in statement. Have you done it? So you are just doing it. Okay? So all the work, research for the last half century has been devoted to these 2-level systems. Okay? Whether it is for the lasers, whether it is for the condensation, whether it is for anything. Huh? Okay? So these are very important. Okay, so let's consider a 2-level system. Okay, now what does that mean? So I'm having only 2 energy levels, okay, at hand. So let me consider a 2-state, sometimes 2-state, okay, 2-state system. Okay. So let me consider these are the 2 states. Okay. So let's write this is your E0. Okay. So I'll put a 0 here. So and E1 0. So these are their unperturbed energies. Clear? Got it? Okay. So let's say we call this as a level 1. Let's call this as a level 2. Clear? Okay, there is a nowadays people are working towards the quantum computers and quantum information. Okay, these two level systems are very important because they act as the units of information, what we call it the qubits. Okay, so that's why you should know these things. Okay. I will be teaching this in the last at the end of this history. Okay, so let's consider this. So if you are okay, how I write the Hamiltonian now? If I am having this two level system, how I write the Hamiltonian? Yes? Linear combination, how? Give me the form. So let me write the unperturbed Hamiltonian as 0. So how I will write? Okay. I need to write the Hamiltonian, okay? So when an operator comes to your mind, okay, so there is a projection of this operator in linear to an object in this mathematics that we call as a square matrix. Okay, suppose you are having, let's say, any operator in your physics, in quantum mechanics, so that you can represent by a square matrix in mathematics. Clear? So this is actually the isomorphism between the two, so you can, they are equally good. Okay, so when I have to write the Hamiltonian, I am having two level system. Clear? So how I write it now? I have to write it in terms of the matrix. Now if you think the hydrogen atom, what you have solved it, okay, without the spin, you have not considered any kind of matrix algebra, is it? But if you have done the harmonic oscillator from the matrix perspective, you have written the matrices. Clear?
Yes.
So you have put actually the harmonic oscillator Hamiltonian in terms of the matrix. Clear? And the eigenvalues of that matrix are actually the eigenenergies of the harmonic oscillator. Clear? Got it? So when you are having a Hamiltonian and you have to write it in terms of the matrix, put the eigenvalues of the Hamiltonian where? As the diagonal entries of that matrix. Clear? Got it? Okay. So let's write it in terms of a matrix. Okay, then I will show you the another way. Okay, so where are the diagonal entries? So since first entry will be the ground state. Clear? So let's write it as E. Okay, so let me write this as E1, so that it is 1, and E2. So you are having E1 unperturbed, then you put the another E2. Is there any transition I have represented? I have not considered any transition from this level to this level or this level to. So the off diagonal terms will give you simply those transitions. Since there are no transitions involved, you put simply 0. Clear? So this is your Hamiltonian for a two level system. Clear? Okay. So this I can write as E1 naught in terms of the, since this forms a basis. So what is the dimensionality of the Hilbert space here? Only two-dimensional Hilbert space, because I am considering only a two-level system. The Hilbert space is two-dimensional. So what are the eigens? Okay, what are the basis states? The eigenstates of the Hamiltonian. So this is your Hilbert space. Okay, got it? So now in terms of these very states, so how I will write it? You make like this thing: E1 multiply with this very, okay, a projection operator like this thing, 1 and 1. Clear? And then you take this E2 naught, multiply it with this projection operator. Clear? Outer product. If you see, so this object is this very entry. So now this 0, 0, 0 and E1 naught. And this will be 0, 0, 0, E2. Clear? Samajh aa? Okay, let me give one more thing to it. Okay, so that you know it. You should know these things. So let me define this one state in terms of a matrix as 1 and 0. This when you write a cat, you always write it in terms of a column vector. Clear? Okay, when you are having a basis set, okay, let's say you are having a basis vector E1 along x-axis. How you write it? You write it as 1, 0, 0. Is this? So this is a vector. If you are having a three-dimensional basis set in Cartesian plane, okay, Cartesian 3D space. So you write the a vector along unit vector along x-axis as 1 0 0. Clear? So now let's put a unit vector along this direction. Okay. So let's call, okay, so that means I have to write this 1 because it forms a basis vector. Clear? So let's write it as 1 0. So what will be the 2? So since this is the only other case, so 0 and 1. These are linearly independent, now you can see. Clear? Okay, so now let's write this 1 and 1. So what is that equal to? So it is 1 0 0. Sorry, 1 0. Okay, so what is that equal to? So it's 1 0 0 0. So this is the matrix representation of this very object. Clear? Okay, so now let's write this 2. So what that is? So it's equal to 0 1 and 0 1. What is that equal to? 0 0 0 1. Clear? Now you can see, put this matrix here. So what you get? E1 0 0 0 plus E2 that is matrix. Got it? Okay. Now let's add a perturbation to this very system. Who said it? Who said it?